So the nature of our upper limit of hearing frequency has to do with these hair-like cells called cilia. For frequencies above a certain value, we just don't have cilia in our cochleas that will resonate with them and send that signal to our brain. We don't have the body parts to detect sounds that are so high in frequency. Now, what about loudness? Well, we have units for loudness too. It's a bit trickier and subjective. It depends on the context. But we use a unit called the decibel, which is, 1/10 of a bell, decibel. It's just that the way it was defined, the bell is not so useful. It's really, really big. And so decibels is the unit that we use to describe loudness. The thing is, absolute loudness isn't so useful for us. And so the decibel is always a comparison to a reference value. Well, what kind of value is the most absolute? Well, it's kind of the opposite as it was for frequency. For acoustic sounds, when we're thinking about sound changes in sound pressure or sound pressure level, 0 decibels gets defined as the quietest sound the average healthy human can hear. And so every sound louder than that is a positive value in decibels. What's the maximum loudness we can hear in decibels? Since a louder sound is making our tympanic membrane, our eardrum, move back and forth farther and farther with each cycle, the upper limit of human hearing loudness is more a factor of the point where hearing damage happens, or at least the threshold of pain. That is generally about 120 decibels away from the quietest sound that we can hear. But that's in terms of SPL, sound pressure level. Well, when we're dealing with the digital signal, it's represented as numbers. It's not a physical phenomenon, and so we're not impressed with how loud it can get. That's subject to our main volume control. So the most solid place to define 0 decibels is not the quietest sound, but just full volume. And so when we're thinking just in terms of a numeric scale, decibels in relation to the full scale of our dynamic range, or decibels full scale, dBFS, 0 decibels is defined as the maximum level that can be output. What happens when we exceed that maximum? Well, we can't express loudnesses any greater than that, and so it gets chopped off. It doesn't have enough digits to represent a number that's this high. It's above full volume. So in a digital representation, every decibel value is negative because it's below 0, because our reference loudness is defined as whatever the maximum is. We call this decibels full scale, dBFS. Now, you may have also seen an analog meter that has 0 somewhere in the middle, close to the top, and so it can have negative values and positive values. You may have seen them as volume unit meters like this one, with lights that go up and down, or with a needle meter that goes side to side. In an analog system, 0 decibels is defined as not the minimum and not the maximum, but the optimal value, or the loudest amplitude that it can capture without distorting the signal. It's going to be failing in certain ways and shaping our sound, not like a digital signal does and coarsely chopping off the tops and bottoms, but giving more natural torn edges to the tops and bottoms of our waves. That won't be a faithful representation of our sound, but might be unfaithful in ways that we might appreciate. We say it gives it character. And so with an acoustic representation of sound, we say dBSPL, decibels in sound pressure level. 0 decibels is defined as the quietest sound, and the loudest sound we can hear is the loudest sound that we care to hear at the threshold of pain or hearing damage, 120 decibels. In the digital system, 0 decibels is defined as the maximum value it can put out. Anything higher is going to get chopped off. And then we can talk about the dynamic range in terms of what's the quietest sound that it can produce. And in an analog representation of sound, 0 decibels is defined as the optimal value, the loudest signal that it can capture faithfully before it starts to add its own natural characteristic distortion. But we could have positive or negative values. In what engineers call dBV, decibels volts, or dBU, decibels unloaded, having to do with the electrical impedance of the circuit. So we've got these 3 types: are dBSPL for sound pressure level, dBFS, decibels full scale for digital signals, and dBV or dBU for analog representations of loudness. Now let's actually listen to it again and think about what it's like between our minimum and maximum values. So here's our sine wave, and I can raise it a little bit. And I can raise it I go up to, say, 800 hertz, and I add 100 to it to get 900, that's a much smaller leap. That's much more close to what we would call a whole step or a whole tone on the piano. So what happens here? As we go up in the frequency scale, the same interval in hertz sounds smaller to us musically. So what can we do to make it equal? Well, it so happens that the way we hear frequency is, we say, it follows a logarithmic base 2 curve. That base 2 means that every time we double the frequency, we hear it going up by one consistent leap, by an octave. So here we are back at 100 hertz. And then if we double it to 200 hertz, it sounds like one leap, and then we can double it again all the way up to 400 hertz. That's another equal leap. Double it again, that's 400 more hertz. And cutting it in half. Brings it down an octave each time. Multiplying the frequency in hertz by 2 results in adding 1 octave to our perceived pitch. So what about our range of hearing loudness? Well, it's on a logarithmic scale, but it's logarithmic base 10. And so we can look at it this way. I'll turn up to full volume, and then every time we divide our amplitude by 10, so I'll go from 1 to 0.1 to 0.01 and so on, we'll see a consistent drop of what happens to be 20 decibels full scale here. And so here we go up to full volume, divided by 10 to 0.1, and we see it drop to 20 decibels, divided by 10 again, and we see it go down by 20 more decibels, divided by 10 again, and it goes down by 20 more decibels, negative 60 decibels full scale.